What if I told you there are two big ways an agent can learn from experience, either by waiting until an episode ends, or by learning while the episode is still unfolding? Today, we'll build an intuition for reinforcement learning as learning from experience, and we'll connect three core families of methods: Monte Carlo methods, temporal difference learning, and the in-between approaches like N-step methods and TD lambda. By the end, you'll know what each one is doing, and you'll have a feel for when each approach shines. Reinforcement learning is a feedback loop. The agent chooses an action, the environment responds with a new state and a reward, and that cycle repeats. Over time, the agent tries to shape its behavior into a policy that earns as much reward as possible, not just right now, but across the future as well. To keep things grounded, imagine the agent as a curious experimenter. It keeps testing the world and collecting feedback. The real trick is turning that messy stream of experience into stable learning. When we talk about the future, we need a way to measure it. That's the return, the total reward from a point onward. Often we discount future rewards a little, so immediate rewards count more than rewards far away. Value functions are our shortcut for predicting that return. V of S tells us how good it is to be in a state. Q of S, A tells us how good it is to take a particular action in that state. Everything in this video is essentially about how we estimate those values from experience. So here's the fork in the road. Do we wait until an episode is over, look back, and then learn from the full outcome? Or do we learn while the episode is still happening, using partial information and our current predictions? And if both extremes have trade-offs, can we combine them in a principled way? That's exactly where Monte Carlo methods, temporal difference learning, and TD lambda fit into the story. Monte Carlo methods are the tell me the whole story first approach. You let an episode play out to the end, and only then do you compute what actually happened. How much reward was collected from different moments along the way? Because the method uses real, observed outcomes, there's something very honest about it. No guessing required. If the agent wants to know how good a state was, it looks at what followed that state in the episode and uses that total reward as the teaching signal. There's a small detail that matters more than it sounds. What if a state appears multiple times in one episode? In First Visit Monte Carlo, we update based on the first time the state shows up. The idea is to reduce the effect of repeated, highly related visits within the same episode. It's like saying, I'll take the first impression from this episode and avoid double counting echoes of the same experience. Every Visit Monte Carlo takes the opposite stance. If a state shows up again, it updates again. This can speed learning in some environments, but it can also make learning noisier because all those updates are based on experiences that aren't truly independent. So you're trading a bit of statistical cleanliness for a potentially stronger learning signal. Up to now, we've focused on estimating values, but in reinforcement learning, values are usually a means to an end. The end is improving how the agent acts. Monte Carlo control commonly uses an epsilon greedy style of behavior. Most of the time, the agent picks what currently looks best. Occasionally, it deliberately tries something else, just to keep learning and avoid getting stuck with a wrong assumption. Over many episodes, that simple push and pull between exploiting and exploring can shape a strong policy. Monte Carlo's biggest advantage is that its learning target is based on real returns from experience, so it doesn't rely on its own predictions to teach itself. The downside is that it needs complete episodes, and it can be slow to provide feedback, especially when episodes are long. It can also be high variance. 2 episodes can look totally different, producing very different returns. Monte Carlo is a great fit when episodes end naturally and you can afford to learn in chunks. It's a clunky fit when the task is ongoing and never really finishes. Temporal difference learning is impatient, in a good way. Instead of waiting for the episode to end, TD updates right away using the reward it just observed, plus its current estimate of what comes next. That second part is the important twist. TD is willing to learn from a blend of fact and prediction. This is called bootstrapping, using your own current value estimate as part of the teaching signal. It's like learning a route while walking it, updating your confidence with each step rather than waiting until you arrive. TD0 is the simplest TD method. After each transition, it nudges the value of the current state toward reward plus value of the next state. In other words, if the next state looks promising and you got a good reward, the current state should be considered more valuable too. This makes TD naturally online. Learning happens continuously as experience arrives. The Monte Carlo target is the true return, but it can be noisy. The TD target is partly a guess, but it tends to be much steadier. That's why you'll often hear the trade described as bias versus variance. Monte Carlo is typically lower bias because it doesn't bootstrap, but it often suffers from higher variance. TD usually introduces more bias because it relies on current estimates, yet it often reduces variance and learns faster in practice. So the choice is rarely about which is correct, it's about which kind of error you can tolerate in your setting. When we move from value prediction to control, we need to learn action values. SARSA is a classic on policy approach. It updates based on the action the agent actually took next, meaning it learns values that reflect its real behavior, including its exploration. That can make SARSA behave more cautiously in environments where exploratory mistakes are expensive, because it knows it sometimes takes imperfect actions. Q-learning takes a different stance. Instead of updating toward what the agent actually did next, it updates toward what the agent believes is the best next action. This makes it off policy. It can learn an optimal target policy even while behaving with exploration. That's powerful, and it often learns strong policies efficiently. But it can also be more sensitive, especially when combined with function approximation, which is one reason modern deep RL spends so much effort stabilizing learning. Monte Carlo looks all the way to the end of the episode. TD0 looks just one step ahead. N-step methods ask a very natural question. What if we look ahead a little bit, but not all the way? In N-step learning, you accumulate rewards for the next N steps, and then you bootstrap from the value estimate at that N-step look-ahead point. With N set to 1, you're basically doing TD0. With N set to the full remaining episode, you're basically doing Monte Carlo. So N becomes a knob that moves you along a spectrum. A good intuition is game playing. Calculating all the way to the end is too slow, but evaluating after one move is too shallow. So you look ahead a few moves, then use your current evaluation to estimate the rest. That's N-step learning, a short rollout anchored by bootstrapping. As N grows, you rely less on bootstrapping and more on real rewards, which can reduce bias but increase variance. As N shrinks, you get quicker updates and more stability, but you lean harder on your current estimates, which can introduce bias. In practice, N is chosen based on the task's episode length, how noisy rewards are, and how accurate your value function is early in learning. Even with N-step methods, there's still a lingering challenge. Rewards can arrive late, but the actions that cause them happened earlier. If learning only updates the most recent step, it can take a long time for credit to flow backward to the decisions that truly mattered. Eligibility traces address that by keeping a kind of fading memory of recently visited states or state action pairs. When a learning signal arrives, it doesn't just update the latest thing, it spreads updates backward along that recent trail. TD Lambda is a clean way to blend the entire N-step spectrum, using a single parameter called lambda. When lambda is close to 0, learning behaves more like one-step TD. As lambda moves closer to 1, learning becomes more Monte Carlo-like, letting outcomes influence earlier decisions more strongly. You can think of lambda as setting the depth of the agent's learning memory. The mechanism is intuitive. When you visit a state, its trace becomes strong. As time passes, that trace decays. Then, when a TD error appears, when reality differs from your prediction, the algorithm uses those traces to decide how far back the correction should spread. Recent states receive larger updates because their traces are strong. Earlier states still get some adjustment, but less and less as the trace fades. The result is learning that stays online, like TD, yet assigns credit across time, like multi-step returns. There are two complementary ways to interpret what TD lambda is doing. In the forward view, it's like taking a weighted blend of many n-step returns, mixing shorter and longer horizons. In the backward view, it's about eligibility traces carrying learning signals backward efficiently. The backward view is what we typically implement because it works online and doesn't require storing and recomputing lots of forward returns. If you zoom out, the story is surprisingly unified. Monte Carlo learns from completed experience, which can be slow but straightforward. Temporal difference learning updates in real time by bootstrapping, which is fast and often efficient. N-step methods and TD lambda connect these approaches into a continuum, giving you a dial for how far learning should look ahead and how far credit should flow backward. And if you keep that one idea, how learning targets trade off waiting for reality versus leaning on prediction, you'll have the right intuition for a huge chunk of reinforcement learning. Like and subscribe if you want the next episode, From Value Learning to Policy Gradients.